Hello there. Have you got problems? Well, I'm Anna Mackay and I'm going to help you try and solve them, provided your problems are about vectors. So in today's video, we're looking at that. Some of the different scenarios you might face with these types of problems, especially in terms of plane problems, as in aeroplane problems, is that we call it the resultant vector. So if we have, in this case, the speed that the plane is moving, but there also might be factors like wind or whatever. The resultant vector is the sum of the vectors involved. Just try to imagine if there was no wind, what would the path be of the aeroplane? It would be moving straight ahead, uninterrupted, no problems. But what if there was wind blowing from the west, for example? What impact might that have? So imagining lots of wind blowing from the west here, what would the resultant vector be? So we represent the wind vector by perhaps a W vector, and that's having an impact, again from the tip, from the beginning there, to the west. Thinking about the resulting vector would be in this direction, and to calculate the impact of that, you would add together A and W to get your vector of R. Some of the terminology to be aware of: airspeed is relative to the air and ground speed is relative to the ground, often represented by A and R. So here we are. If we have an aeroplane that must fly from Adelaide to Sydney at a ground speed of 600 kilometres an hour. So try and imagine this. Sydney, let's say approximately, is east of Adelaide. But we have wind blowing at 50 kilometres an hour, and for the purposes of this simple question, we'll say constantly from the northeast. So imagining where that is blowing from. So we're asked to calculate in what direction and at what airspeed must the train travel to get to Sydney. So if it was flying directly, it would obviously move in an easterly direction. We'll call that R, 600 kilometres per hour. But the wind coming from the northeast is represented, say, going that way, W for wind, and that's 50 kilometres an hour. So our resultant vector that the plane would travel in is, we have to add on that wind factor. So if the wind was acting like this, the resultant vector, it would be going in the opposite direction, wouldn't it? So to take it into account for the wind, we would actually have to subtract off the wind. So we'd have to go in the opposite direction of the way the wind is blowing in terms of mathematically calculating this, so that our resultant vector is heading essentially what's a northeasterly direction, because if we don't, otherwise the resultant vector would head down in a southeasterly direction. So as I was saying, we have to take into account negative W there for that resultant vector. Okay, doing one example here. In still water, Jacques can swim 1.5 metres per second. Jacques is at point A, at the edge of a canal, and considers point B directly opposite. A current is flowing from the left at a constant speed of 0.5 metres per second. So we've got two parts of this. The first part is if Jacques dives in straight towards B and swims without allowing for the current, what will his actual speed and the direction be? So hopefully you're trying to visualize what would happen. He wants to try and swim straight across the river, the canal, but that's not going to happen because he's got a current, he's got a force acting on him that's going to push him towards the right. And we want to find out, well, what would the resulting impact of that be? His speed of 1.5 metres per second, is that going to be increased or decreased? And the direction would he end up in? Would he be straight towards B? No, he'll be off to the right-hand side. So let's calculate these things. Some things to bear in mind: we're going to use C as the current's velocity factor. So C for current, 0.5. S is the velocity vector Jacques would have if the water was still. So that's his speed that he can swim. So S for speed, 1.5. And F is the result of the two of those combined. Let's have some space to work this out now. Okay, so we need to, I guess, create a bit of a picture here. So on this diagram, we want to essentially work out the impact that it's going to have here. So we're going to call this F. Let's label where our other two vectors are. The S for the speed that he can swim, would be this vertical one here. We're calling that S. And the impact of the current, C, we label there. So two things. To work out speed, what is that? The speed is of F here, so that's that length. Well, what do you notice? We've got a right-angled triangle there. How do you work out the length of F? F is the hypotenuse, and so therefore we're going to set this up like this. We need the modulus of each of these factors here, and it's the square of each side. So let's have C squared adding on S squared, and we're going to calculate that. C was 0.5, squaring that, adding on 1.5 for his speed, and we get 2.5. Don't leave it there though, because that's F squared. So we're going to square root 2.5 to approximately get 1.58. So the speed is approximately 1.58 meters per second. What was his speed on his own without any resistance? I think it was 1.5. So his speed, as you can see, has increased because of the effect of that current. And the direction. Where is that? Well, direction is represented, I suppose, by the angle that's within here. So we need to work out that angle in that right-angled triangle. Well, you have a right-angled triangle, and here is your angle. So think about what each of the sides are relatively. F is our hypotenuse, or we have the opposite and the adjacent. Now, my tip is, yes, you could use the hypotenuse and use sine if you like. However, that was the one that you calculated. Now, just in case you made an error while calculating that, you don't want to compound that error by using the wrong number in the second calculation. So whenever in these situations, stick with the numbers that you've been given. So we know C and we know S. So that would be the opposite and the adjacent side. So I'm now going to use that in tan. The opposite is 0.5 over the adjacent side, which is 1.5, using inverse tan to get 18.4 degrees. So therefore our direction is approximately 18.4 degrees to the right. So that's the impact of the current if Jacques doesn't take it into account. The second part here, just putting the question back up here, and part B. He wants to swim directly across the canal to point B. So that's his aim. So at what angle does he need to aim to swim in order that the current will correct his direction? So I'm sure you can anticipate he has to aim somewhere out to the left here and swim at the speed that he can swim, 1.5 meters per second, and allow that current to help drift him back so that he ends up at B. And so we have to work out the angle and what his actual speed will be. So again, we're going to draw a right-angled triangle. Now you might ask yourself, well, how big does this triangle need to be? Do I need to draw a small one? Do I need to draw one that goes all the way across to the other side of the canal? It actually doesn't matter. Because the speed of the current and Jacques' speed are constant, they're not changing, I guess it doesn't matter if you've got a small triangle, a medium triangle, or a large triangle there. They're all similar triangles. So the ratios of all the sides and the angles will be in proportion to each other, and so therefore that impact will take itself into account. So you don't have to worry about that. So I'm just going to create us a bit of space here. Now let's draw a right-angled triangle here. So what do we know about this one? To work out the angle, this is the angle in here. Let's use a different symbol, phi this time. Well, we know two of the sides. We've got C for the current here, 0.5, and his speed, because now on the hypotenuse, that's where Jacques is going to be. He's going to swim there. And the resulting vector of that will be F. So his swimming and taking the current into account, that will end up getting him swimming in a straight line. So to work out this, the angle, we're actually going to use sine this time. Now sine is opposite over hypotenuse. So the opposite side is C and the hypotenuse is S. So for that we've got 0.5 over 1.5. Using inverse sine, we approximately get 19.5 degrees. So what was the question? At what angle should he aim in order that the current will correct his direction? Aim for 19.5 degrees. In which direction? To the left of B. So that's what he needs to aim for. And what about his speed? Well, speed is that F, it's the resulting vector there. So it's essentially Pythagoras. We've got a right-angled triangle and we want to solve for one side of that triangle. So setting that up, the two shorter sides are f squared plus c squared, taking the modulus of those for the positive values is equal to s squared. Substitute in what you know. We don't know f, but we do know c, 0.5 squared, and s is 1.5. And solving for f, notice that last time round we were solving for the hypotenuse, and this time round we're solving for a shorter side. And square rooting that, therefore we get for f approximately 1.41. What is that? Dollars? What units is that? So that's his speed. So the speed is approximately equal to 1.41 meters per second. Was that slower or faster than what Jacques could swim on his own? So it's slower because he has to work against the current. So his relative speed ends up being slower than him swimming directly across, which is what you'd expect. So I guess there's a little tip. If you ever get an answer there that is higher than what his speed would be without the current, that should be a sign to you that you've done something wrong. Okay, join me in the next video. 3i, the scalar product of two vectors. Subscribe to the channel if you haven't already and give it a thumbs up. Thank you.